Welcome to Statistical Computing with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll get started with the ideas of data visualization and how to implement them in R using the Grammar of Graphics package by Hadley Wickham. So here we are at the course website. I'm going to page or scroll down, and we're looking at this section here for visualization. Here are the slides, and let's get started. This lecture is broken into two parts. The first part is going to focus on data visualization, primarily pulling ideas from Edward Tufte, though there's so many resources out there, including a chapter I've recently written with Melina Allen on the topic. And the second part of this lecture is on using R and the Grammar of Graphics package, ggplot 2, to implement many of these ideas. So Tufte has had a lot to say on graphical excellence in his the visual display of quantitative information. My apologies, I had to look back on my bookshelf. He suggests that excellence in statistical graphics consists of complex ideas communicated with clarity, precision, and efficiency. Graphical displays should, first of all, show the data. If you're not showing the data, you're already doing a disservice. Second, if you're making the viewer think about how you made that design, then you're distracting from the content. So let them focus on the substance. Okay? Try to avoid distorting what the data have to say. Try to increase the resolution to present many numbers in a small space. If you have a large and complicated data set, try to make it understandable. Encourage the eye to compare different pieces of data. And we're going to see these. All right, let me keep going. Reveal the data at several levels of detail. So from the broad overview to fine structure. And try to serve a reasonably clear purpose. Are you describing the data? Are you exploring the data? Are you providing some tabulation and summaries? Try not to be decorating the data so much. And be closely integrated with the statistical and verbal descriptions of a data set. So you can plot the data, you can put a regression line over a scatter plot, for example, and you might incorporate other text in there to indicate which hypotheses you're testing and so on. All right, so why plot data at all? So here's a very clear example of how numerical summaries can lead you astray. So Anscombe's quartet, which comes from he's the author of a paper that introduced 4 data sets. Here they are. We've got 2 columns, X and Y, and there's 4 separate data sets here. I'm going to read this into R and reshape the data a little bit, and going to calculate a bunch of numerical summaries. They're commented over here in the right. We're going to look at the sample size, the mean of X, the mean of Y. We're going to fit simple linear regression, look at the regression coefficients, the standard error of the slope, the t-statistic of the slope, the x sum of squares, the residual sums of squares of y, the regression sums of squares, the correlation, and the r squared for the regression. Okay? 2, 4, 6, 8, 10, 12 different numerical summaries. And we can present that as a table. So here are those summaries, and you can pause the video here if you want to look a little bit more closely. But I'll tell you that pretty much for each of the 4 data sets, okay, so data sets 1, 2, 3, and 4, as you scroll down at least to 2 decimal places, almost all of these are identical. There are tiny differences for a few, but if you were to see one column of numbers for your data set and not the others, you know, they're effectively the same. Let's plot it. So I've plotted the 4 data sets. I've overlaid a regression line just for emphasis. And you can see these are wildly different. In number 1 is probably what you would be thinking of for a standard scatter plot. But in those summaries on the previous page look pretty good. We've got an R squared of about 67%, correlation of 0.82. We have a positive slope. Let's see, intercept of 3. This is probably the slope here of 0.5. And so that's what I would imagine when I looked at those numerical summaries. However, I didn't plot the data, I didn't look at the residuals, and clearly we've got 4 distinct data sets. We've got a quadratic in number 2. In number 3, we basically have a straight line with one outlier in the y direction. And in number 4, we have all the points with the same x value except one outlier in both the x and the y direction. So clearly plotting is a very important addition to just calculating numerical summaries. So Menard has produced a very popular plot to discuss in data visualization. There's a lot of good things about it, and there are some criticisms. Many of you have probably seen this. It is Napoleon's march on Moscow, where they start, in fact, I usually need this plot here. In Lithuania, they head east to Moscow and then they retreat. And if I come back to the original graphic, the width here describes what the size of their army is as they head forward. And the black indicates when they start to retreat. And there's some additional information. There's these vertical lines here, which go down to a plot down at the bottom, or an axis down at the bottom, which talks about the temperature. And I think this is degrees below 0, and it gets very, very cold, and the temperature ends up killing most of Napoleon's army on the retreat. Now, there's a lot of great things about this plot. It tells a story just by looking at it. It also has a lot of different dimensions of data in a single two-dimensional display. It is not that readily understood. You sort of need to look at it and take your time to understand the story. So that is one possible criticism of this plot. This is a depiction of this in that you can plot yourself. And I actually have a lecture later on in mapping where I show how to do this. But it does provide a lot of information in a very little amount of space. And it takes a little bit of time to get those ideas, but it would be hard to think of a display that does better for all the ideas that are in that space. So there are 2 essential problems in the display of information. One is we have data that's multivariate, and for practical purposes we only have 2 dimensions to display that information in. So we really have to think about how to get the high dimensional onto a low dimensional surface to reveal ideas. And the second is resolution. How much can you actually fit on a page and have it still be understandable? And let's try not to waste too much space when we display data as well. So here are 9 principles that I'll be covering in this lecture. The first is to enforce wise visual comparisons. 2 is to show causality. 3 is we should try to be as multivariate as our data are in our displays. 4 is to integrate words, numbers, and images together to tell a story. 5 is to, most of what happens in design depends on the quality, relevance, and integration of the content. 6, information for comparison should be put side by side so your eye can easily make comparisons. 7, use small multiples. It's a very efficient way to make those comparisons. 8, don't dequantify your data. If you've got continuous numbers, don't break them into true, false, yes, no, big, small, things like that. And thinking and designing are as one. When you are designing a visualization, you are thinking about the content, and you'll make better decisions as you're creating those visualizations. So, one caveat down here, the principles should not be applied rigidly or in a peevish spirit. They are not logically or mathematically certain. It's better to violate any principle than to place a graceless or inelegant marks on a paper. Okay. Most principles of design should be greeted with some skepticism. Okay, so if you can get a lot of these true inside a visualization, you're doing pretty well. And it's okay to violate them if you know what you're doing. So, enforce wise visual comparison, number 1. On the left we see 2 axes. We've got a horizontal axis and a vertical axis. The horizontal axis doesn't have a label, but these are years. And the vertical axis also isn't labeled, but is in this key over here. It says Connecticut traffic deaths. So in the state of Connecticut, we have over 2 years, we have before stricter enforcement and after stricter enforcement. And this plot by itself suggests that because stricter enforcement was implemented, that had a good effect on traffic deaths in Connecticut. Now, I want to know, compared to what? So in the right, we have more historical data. So we've got more years now, and we have a broader scale. And we see that Connecticut traffic deaths were pretty low, and we had one bad year. And there may be some explanatory cause, like lots of snow that year in the Northeast. And then it came down. In fact, these 2 or 3 numbers are still fairly high relative to what it was in the previous years. So, did stricter enforcement have that effect? It's not clear now. So, one can imagine on the left very different representations of other possible timelines, right? This decrease that we saw in the previous plot on this dark line could just be this, zigzag pattern. Or maybe we had one blip. Or maybe we actually had, which is what I think this story is trying to say, before enforcement and after enforcement, maybe you want to believe that it was at this high level, we increased enforcement, and it decreased to this lower level. So in the context of other states, the plot on the right shows that it looks like Connecticut is basically sort of similar to these other New England states in the Northeast. New York's not part of New England, but these other 3 are. So, compared to what? That's the important principle there. Elena Allen and I have one of our papers on data visualization shows this plot, which is to seek comparisons, but also to encourage you to show more and hide less. So the leftmost plot, plot A, is a very common plot. You take, say, 3 conditions, you observe, say, 50 observations with each condition, you calculate the means, and make a bar plot, put a standard error bar on there, you're done. You might show the result of a hypothesis test at this point. So it turns out in this case, these 3 basically have the same mean. Okay, end of story. End of story until you plot the data distribution. So plot B gives us, in addition to the mean, I'm going to zoom in here. In addition to the mean and standard error, which have also been plotted here, there's a dot with a gray bar. We've also plotted the data distribution. So it looks sort of interesting here. Group 2 is clearly right skewed, whereas the other two are somewhat symmetric. In fact, but group 3 has sort of a short tail on the upper side. So these data distributions are not the same. If we do show even more, so we've got the box plots on here, but we also have these gray violin plots. It's basically a smoothed density curve, which is made symmetric. And one thing you can see is number 1 is, is a distribution that's not quite normal, but, it's symmetric and there aren't really any outliers. 2 is skewed to the right, and 3 is bimodal. So the question here is it interesting to compare means as we did in plot A? The mean is not the interesting feature here. The data distribution is the interesting thing. I want to understand this bimodality, or what makes condition 2 skewed to the right and not symmetric like condition 1. So the more you show, the better answers you can provide and the better questions you can ask. All right, show causality. This sometimes we don't really get an opportunity to do because there's a lot of work done that's associative rather than causal. But there's a famous map by John Snow from the 1850s where there was an outbreak of cholera. And so we have this map, and what they did, I'll zoom in a second, but we've got red dots wherever there's a water pump. Okay, and people would walk to the water pump, fill their containers with water, and bring it back to their homes. I'm going to zoom in on this plot. And we've got dark lines which indicate deaths on different city blocks. Okay, so for example, and you can see my little cursor in the bottom left. We've got one city block here where there's one house with a lot of deaths, and then 2 with just a couple deaths, and then we have like 1 death here, 1 death here, 1 death here. Okay, but you can see that if you're looking around the city at what's causing the problem, there's a lot of focus around this one central water pump. Around all the other pumps, there's almost no deaths. So that's a suspect because you plotted the data. And you knew which data to plot. You knew to plot water pumps and number of deaths. So here's the outbreak, basically September 1st, number of deaths per day. And man, look at the y-axis. That's 100 people. On the 8th day, they removed the water pump, or the handle from the water pump, so no one could get water from there anymore. And maybe the deaths were trickling off anyway, but they slowly went down. So they found the cause and they remedied it through visualization. All right. Number 3, the world we seek to understand is multivariate, and our displays should be also. Recall that Napoleon's March on Washington plot. It had 6 different dimensions. It had the size of the army as the width of the lines. We had the X and Y dimension as latitude and longitude. We have the direction of the march because over time there are dates on that path. There's the temperature data at the bottom, and dates, that's time. So we've got at least 6 dimensions on that plot. Okay. Number 4, integrate words, numbers, and images. So in brain imaging, this is a common plot on the left where we're looking at EEG signals. EEG is electroencephalography. You put little electrodes all over the scalp of your head, and it measures electrical impulses. And so on the left we have an experiment where we have time along the horizontal axis, and we have the average independent component potential. This is basically the magnitude in microvolts of the response. And in this trial, you are shown something and you're asked to respond. And if you answer correctly, the average over many responses, so this is time synchronized or time locked responses, you would perform this experiment maybe 50 times, and of the ones you got correct, the average time course is the blue line here. And whenever you make an error, that's put into another category, and the average of those is this red line. So you can see when you make an error, you seem to have a larger response than when you get it correct. I'm going to scroll over to the right and see what you can do better. So look at all the annotation. We still have the error line, or the error and the correct labels for the red and the blue lines, but we've added a bunch of things. One, we've added this line here for the target, and negative 200 milliseconds are flankers. So these are basically different stimuli, and the target is when you see the thing you're supposed to respond to and you push a button. And what we see is, so that helps us indicate what the stimulus is as we come up to the moment. Then we've also added error bars, pointwise 95% confidence intervals for each of the lines in the light red or a light blue around the line. At the bottom, we have hypothesis, the null hypothesis and the alternative hypothesis stated for what test is being performed, and then the p-value and ranges where in fact these two curves are different at a 0.001 level. So there's a moment about 400 milliseconds in that's different, where the error is much lower than the correct, and then right around 500 the error has a higher response than the correct. So we're able to understand a lot more from this plot than the first plot, because we've added annotation into the plot. And it didn't get in the way. It doesn't feel cluttered. Here's another display. This is standard for functional MRI, where we're asking, in this case, we have two conditions. This is an audio oddball task where you hear different sounds, and sometimes there's a standard sound that's like a pip, like just a beep, beep, and then there's a novel sound that sounds like a train whistle, or a sweeping noise like whoop, or something like that. And there turns out that you have a big response when there's something new. Okay, so here novel minus response, or novel minus standard, is a contrast between those two conditions. And what we see is in the auditory regions, which is actually close to the ear, we see a strong positive beta weight. So there's a meaning that novel is greater than standard in those areas. And underneath there's a gray structural image which shows a T1 weighted image of the brain. So white matter appears white, gray matter appears gray, and the ventricles are black. That has your cerebral spinal fluid in it. And what they do is that we've got this color bar, and you put a threshold. So there's a threshold right around the yellow area or the blue area, and anything greater than that threshold is displayed. And that allows you to see both the structure and the larger regions. So what Elena and I have proposed, and we wrote a little R function for it, she did, is to show more. And so what we've done is we've made a color bar. Instead of using a one-dimensional color bar, which only has the colors, we have a two-dimensional color bar, We have the color, which gives you the beta weight, but we also have a vertical part of the color bar, which shows you the absolute value of the t-statistic. So if your t-statistic is close to 0, that's an area where the novel and the standard are not very different from each other. And so we're going to have a lot of transparency for the color. So you can see, regions in the middle of this image, you can see right through there, and you can still see the structure. And as the t-statistics gets larger along the y-axis of the color bar, the color becomes more opaque because it's more important to us to see what that color is. And so in those dark regions, you can't see through those colors, and you get a bright display of that color. And we have some annotation here. We have the null hypothesis and the alternative that's being displayed. And we also have a shape. Okay, this little outline indicates where the p-value is less than 0.001. So these circular outlines are the same areas that were displayed on the left. In fact, this z minus 19, which tells you where in the brain we're taking a slice, that is the same as this. Okay, z equals 19 on the right, and the outline here is exactly the shape that's on the left. Okay, so we've gained so much more. In fact, the thing that we've gained is that there seems to be not only this positive response on the left and right sides of the brain, but there's also this blue response in the frontal lobe, and then there's 3 regions in the back of the brain which are negatively correlated. And that happens to be called the default mode network. It's a set of regions that tend to be deactivated when you are engaged in an activity. And when you start to daydream or something, that's your default mode becoming more active. So we've gained a lot. Furthermore, we've added a second scatter plot, which shows for each of those regions, for the left and for the right, we have a standard along the horizontal axis, we have the novel along the vertical axis, and a scatter plot of those. And you can see that the novel points are the points are higher for the novel dimension than the standard, and that's what's being shown. We've got 28 subjects here. So show more, hide less. That's our principle. And I'm going to skip another plot that shows the same thing. Number 5. Most of what happens in design depends on the quality, relevance, and integrity of the content. And I'm sorry, but if your numbers are boring, you have the wrong numbers, is what someone else has said. Design won't help, it's too late. So I guess this concept is about solving interesting problems. All right, information for comparison should be put side by side. So back in the early 1600s, Galileo published a book that where he had discovered sunspots and the rings of Saturn. And so this data set is about the sunspots. So I'm going to zoom in on one of these figures, and each of these circles represents the sun and a date. So we have the 23rd of October, and then the second one is 24th of October, and so on. So these are a version of small multiples, which we're going to talk about in a second. And we have the sunspots labeled, and as we zoom out, we can see how that string of sunspots, A through E, is actually shifting around in the display. And so we're now able to see what, not just one static image of sunspots, but actually that the sun is rotating and the dynamics of the situation. This is another way of visualizing sunspots. It's a poorly labeled plot, but it's interesting and dense, so I want to discuss it. Along the horizontal axis is time. It starts at 1880, and it goes all the way up to 1980. And we've got 2 sets of y-axes. At the top, we have the latitude of the sun. So we have the equator in the center, and then we have 30 degrees north and 90 degrees north. So this is not a linear scale. It may be scaled proportional to the area that latitude represents on the sun, but that's not discussed. So that would be a criticism that I have. And one thing, and we also have color for the sunspots. We don't, that's a third axis. We need a color bar, okay? But clearly yellow is higher than red, and red is higher than gray. Presumably gray indicates no sunspots. And one thing we see is that the sunspots have these cycles, and they tend to start at around, say, 30 degrees north or south, and over time they trickle toward the equator before another sunspot cycle. At the bottom, we have another axis, which is the percent of area of sun covered by sunspots. And this is not a linear scale. Okay, you can see this is, well, it's very small. You can see that it's very small. If I zoom in here, that axis starts at 0.1% and goes up to 1.0%. But down here it must be something close to 0%. I think this is a logarithmic scale. And the obvious thing here is that we seem to get these cycles and that stay roughly less than 0.1%. But something happened around 1920 where the cycles got larger and larger up until about 1960, where it seemed to return to this baseline. So a lot of information in a small area. It tells an interesting story. Number 7, use small multiples. So we've seen this before. Small multiples is, they go by other names, a trellis plot, a lattice plot. Facets is the name that ggplot uses. And the beautiful thing about small multiples, if I scroll in down to Anscombe's quartet that we saw before, is once you understand one of the displays, right? So if this bottom left one, we say the x-axis goes from about roughly 5 to 15, y-axis from 5 to about 12.5. Now I understand one of the plots. Immediately I understand all of them, and my eye, without even thinking about it, starts making comparisons. It's beautiful. All right. Number 8, don't dequantify. Numbers have meaning. Try not to reduce them to binary or categorical data if you can help it. Sometimes it's necessary, but you lose information, you lose resolution when you go from a continuous number to a discrete number. Of course, we all know that all numbers are discrete, right? Anyway, number 9, thinking and designing are as one. So if you start putting your pen to paper and thinking about how you want to display your data, you're really actively engaging in thinking about your data. And sometimes you can reveal really important ideas just through figuring out how best to visualize that information. All right, good design is a lot like clear thinking, and these are not my words. Bad design is stupidity made visible. So if a chart has 3 phony dimensions to compare 4 numbers, it shows the person doesn't know what they are talking about. That's one of the major criticisms about 3-dimensional pie charts, for example. You have 1-dimensional data that you have projected onto 3 dimensions. All right, there's lots of examples of bad. I'll let you scroll through and look at these. This first one has to do with where the 0 is. So there are numbers on these bars, 3 million, 4 million, and so on. Where's 0? You might think that it's at the bottom here, but actually, if you were to project this axis, I think the 0 point is at negative 4 million. So these bars are actually more different than they appear. And the images behind are sort of distracting from what the content of those bars are. Here we have a plot about commissions paid to travel agents. And unless you looked really closely, you probably would miss this label down here that says first half of 1938. It looks from first glance that, oh my God, the last 2 years have been increasing and the third had this major decrease, but that's only the first half of the year. So these is not a fair comparison. This is a crazy plot about distorting the axes. So I'll let you go ahead and look at this. Go ahead and press pause and look more closely. And I like this plot so much because this first plot on the left is very simple and clean. And what they've done on the right is decorate that plot, but haven't distorted the informational content of the plot. So go ahead and do whatever you like, but don't distort my data and lie to me. So that concludes the first half of this lecture on data visualization. We'll come back in the next video and talk about producing beautiful plots using the ggplot package in R.